So the first equation we're going to talk about in this section is to define or describe or determine the magnetic field of a moving charge. So just to show you, I showed a short video clip in the previous video, and I just want to remind you, this video clip, we have this wire that will be carrying current. As we start the video, it is not. So all of these little rings or discs contain a compass needle. A compass needle is just a tiny little magnet, and right now those little arrows point in roughly the same direction, and they're pointing towards the Earth's magnetic North Pole. Sorry, the Earth's magnetic South Pole is what they're pointing towards, which is relatively close to Earth's North Geographic Pole. As a reminder, though, when we turn on the current, these needles now respond more so to the magnetic field of the current flowing in the wire. And that's because the magnetic field that this wire will create is stronger than the Earth's, and thus it has a larger effect on these needles. So I just want to show that initial alignment, and then we'll carry that back to talk about our moving charges.
I have a wire that goes through a piece of cardboard here, and I've got it surrounded by little tiny compasses. They're all pointing generally this direction. And I'm going to run current through the wire that will be coming up the wire this way from underneath. So based on the right-hand rule, there should be a magnetic field around this wire. In which direction? Let's find out. So I'm going to clip this on now. So it looks like all of the arrows are tending to go around in a counterclockwise fashion from this perspective.
Okay, so these little compass needles are lining up tangent to the circle that would represent the magnetic field. He mentions a right-hand rule, which we're going to talk about as well. Okay, so I pulled a couple pictures from your book. This is just from our textbook. This on the left is a wire carrying current. So this wire has current either flowing up or down. I'm going to draw it as if it were up. In this particular picture, we cannot tell because those are not compass needles. These are iron filings. So these are little tiny pieces of iron on some sort of white surface like the cardboard. And they have lined up to align with the magnetic field around the wire. It turns out that the magnetic field around a wire is a circle. It's a complete circular path. And the magnetic field, the direction has to be determined by a compass needle, one that we know the direction of. So the right picture here is essentially describing what we just watched. Originally, those needles will all roughly line up towards the Earth's geographic pole because that's close to where the magnetic South Pole is. If the current is strong enough, so they're showing us that this current is flowing upwards, those compass needles align tangent. So they're essentially showing us that the magnetic field around a current long straight wire like this, a straight wire, is just making circles. And since the direction of those circles is always the same, we can use what we call a right-hand rule. Right-hand rule. If we point our thumb, now number one, you have to use your right hand. That's why it's called the right-hand rule. I say that a little bit sarcastically because we often want to try to use our left hand. For those of us that are right-handed, we often try to use our left hand because our right hand has a pen or pencil in it. regardless of whether we're right or left-handed, doesn't matter. We have to use our right hand for this rule to work for us. So we put our thumb as if it were just the wire, and our thumb pointing, imagine there is an arrow on the tip of your thumb here. So your thumb points that way. We put that in the direction of the current flow. And then imagine the fingertips also have arrows. Your fingertips, if you look down at your hand with your thumb pointing at your face, your fingers will curl around in a counterclockwise direction in this case. If looking at thumb. So, meaning if I look down from this direction at my hand, so my thumb is pointing at my eyes, my fingers curl in a counterclockwise direction. They represent these little compass needles. And so the overall magnetic field, the full circle, the compass needles are only showing us the direction at one location. But if we extrapolate from that, we find that the magnetic field makes full-on circles around the wire. So this is something that experimentally we can see. And building off of that, we know current is defined as far as we're using it. The traditional definition as the flow of positive charges. So current is the rate at which charge is flowing. In our circuits, we've said that we're still going to just use this traditional definition. And so we're treating it as if there's a net flow of positive charges in that direction. So building on this, it turns out that current flow, this right-hand rule, allows us to figure out how the magnetic field will circle around a positive charge as well. So how the magnetic field circles around the current carrying wire, but also how the magnetic field will circle around just a positive charge that is moving. Okay, we'll get back to the equation that describes magnetic field around a wire. This wire, we could write this as a bunch of concentric rings, which mine isn't very concentric, but the magnetic field will make complete circles around the wire. It will get weaker the further away we get from the wire. But the field lines are continuous here. Just like around a bar magnet, magnetic field lines are continuous. They don't start and end anywhere. So coming back up just to talk about a single charge, again, building off of this current, since we've defined current as the flow of positive charges, if I have a positive charge moving in the same direction we had the current moving in the example below, we would see that there's a magnetic field created around it that goes counterclockwise relative to this velocity. This same right-hand rule applies. We can put our thumb in the direction that this positive charge is moving in, and then our fingertips represent these arrows and the direction around the charge that the magnetic field, B, so magnetic field is capital B, the direction around the charge this magnetic field will circle. So if I had a positive charge, for example, instead of moving straight up, was moving to the right. If I put my thumb in this direction to the right, my fingertips show circles this way. So this down here into the board there. So three-dimensional is a bit hard for me to draw. Essentially, if I was to draw this as a cross section, so same picture, I could say that the magnetic field up here is coming out towards me. Right? Hold your hand up, your right hand up in front of your face with your thumb pointing to the right, to your right. If you hold your hand up and you just have your fingers, your hand relaxed of sorts above you, your fingertips point towards you. That's what we mean here. The circular path at that exact location tangent to the circle would point out towards you or towards me, any of us that are looking at our hand. If we contort our wrist kind of crazy to try to get our fingers below our thumb, we would see our fingers pointing away. So these circle, this dot and this X are a way we represent the vector direction. So drawing a vector to the right is easy enough. A vector up, down, those are easy to draw on this two-dimensional screen. Three-dimensional is a bit more challenging. So a dot represents out of the screen or out of the paper, pointing towards us. It's as if the vector were just seeing the tip of the arrow. The X represents away from you. If you were shooting an arrow, like a bow and arrow, you would see the crosshairs, the feathers at the end. And so we use the X to represent away from you. That is a general thing. You'll see that throughout the textbook as well. You'll see a dot to represent a magnetic field coming out of the paper towards you, and an X pointing into the paper away from you. We could also represent velocity. So this same example of our positive charge moving to the right, I could change my perspective and say that I'm looking at the positive charge moving towards me. So I would have this positive charge, but the dot here would represent the velocity. And right hand rule, we put our thumb of our right hand in the direction of the velocity. So essentially, point your thumb at your face. So that would mean this charge is coming right at our face. When you do that with your right hand, your fingertips are curled like this around your thumb. Now, they don't go all the way around, of course, but they represent the direction of the circle around the moving charge that would represent the magnetic field. So if a positive charge is moving towards us, we would see the magnetic field making these counterclockwise circles around this positive charge. So this is all based off of what we're calling this right-hand rule. The velocity, the motion of this charge determines the direction of the magnetic field. Now this charge will also create an electric field. Do you remember what that would look like? Electric field points away from positive charges. The electric field points radially outwards. The magnetic field makes circles around the charge as long as the charge is moving, and thus would be perpendicular to that electric field. Okay, our equation, though, that describes and allows us to calculate the strength of the magnetic field around a moving charge looks like this. Mu naught is a constant. Our author gives us a rounded value. It has an exact value that is the value I remember. So when I solve problems, I will use the exact value. But you can also use the rounded number. In our test notes, this is written out, 1.275 times 10 to the negative 6. The units are Teslas. So the capital T is a Tesla. Those are the units for magnetic field. So Teslas times meters over amps. So capital A for amps still. This is a constant we will see a lot for our magnetic field equations. Q, of course, is the charge itself. V, this is the velocity of the charge. The charge must be moving to create a magnetic field. Now, R hat and then R squared in the denominator. If we come back to this top left picture, our positive charge just moving straight up. R is the straight line distance from the charge to some point where we want to find the electric field, the magnetic field. So that's similar to electric field. Electric field, our equation was, actually I'm going to write it with our epsilon naught, only because I wanted to remind you that epsilon naught we saw a lot with electric field equations. So the electric field depended upon the charge. R squared in the denominator was that straight line distance from the charge to the point we were trying to calculate the field. That's similar. We get an inverse square law here as well. R squared in the denominator. R hat just points along this line towards this point over here is where we want to find the magnetic field. So R hat just points over to that location. So R is how far away, or let me put it better, distance from Q to point where you want the magnetic field, and R hat just points along that line. Now, this is a cross product equation. You've seen cross products. As far as physics is concerned, we saw cross products when we talked about torque. They use the term moment if you're taking statics and dynamics. So torque or moment was an R crossed with F. R and F, the cross product only multiplies the components that are perpendicular to each other, and the result is a vector that is perpendicular to both. Applying that here, we have V crossed with this R hat. We only get a result for magnetic field at a point that is perpendicularly away from the velocity. If the point that I was trying to find the field was, say, right up here, at this point, R hat, because R would just be the distance from the charge to that point, R hat would lie along that line. The V and the R hat would be parallel. We would come up with an answer of 0 when we solve the cross product. If you recall, cross product equations can be written also as the magnitude of the vectors multiplied by the angle, sine of the angle between them. Phi is the angle between the velocity vector and the R hat vector. R hat, though, is a unit vector. It still means radially away, right? We're drawing this R hat in our picture on the left radially away from the charge. It's a unit vector, though, so it only has a length of 1. So its magnitude is 1, which is why if I write out the magnitude of the magnetic field, we don't see R in the numerator. The strength of the magnetic field will depend upon our constant, mu naught. It will depend upon the magnitude of the charge, how fast, so just the speed, how fast is this charge moving, phi, the angle between V and R hat, and then it will depend upon how far away from the charge. If V and R hat are parallel, phi would be 0 degrees. And thus, sine of 0 would be 0. There'd be no magnetic field anywhere along the line of velocity. The strength of the magnetic field depends upon how fast the charge is moving and how far away we're trying to measure. So let's go through some examples and looking at both the direction and finding the strength of this magnetic field. All right, let me scroll down here so we have some space to work with. Let's say we have a positive charge, so just a proton. Let's just say it's a proton moving to the right. I'm just going to make up a velocity. So 6 times 10 to the 6 meters per second to the right. So that number is totally made up by me. 2 places I want to find the magnetic field. So point A, a distance of 3 millimeters above the charge. So we're going to find the magnetic field created by this proton at points A and B. I'm going to give us a point B. Let's say point B is just a little bit to the right. So it's still 3 millimeters above the charge, But let's make it 3 millimeters to the right as well. So 2 different points. Now, the fundamental equation for describing the magnetic field or calculating the magnetic field of a charge moving is this. So we just talked about this. This is the fundamental equation in vector form. The magnitude of the magnetic field, any cross product equation can be written as the magnitude of the vectors times the sine of the angle between them. So in this equation, we would just want the magnitude of the charge, the magnitude of the velocity, and then phi will be the angle between v and r hat. Okay, let's look at point A first. Point A, we already know the velocity is drawn to the right. The r is just right here. R hat just lies along r. It points radially away from the charge. So the angle between v and r hat is 90 degrees in this case. V is to the right, r hat points straight up to point A. So the strength of this magnetic field, I'm just going to use this top equation, mu naught. Again, I remember the exact value. You can use the rounded value given in the test notes or in the textbook if you have that open as well. The charge of a proton is 1.6 times 10 to the negative 19 coulombs, which we can also get off the test notes or in the book. So that is the mu naught, that's Q. I need V now. V I made up, 6 times 10 to the 6 meters per second. Sine of 90 degrees, because that is the angle between r hat and v, over 4 pi. R, I also made up, 3 millimeters. So the distance to point A from the charge is 0.003 meters. And that needs to be squared. Now, one benefit of using the exact value of mu naught is that in this case, the 4 pi's are going to cancel. And that just minimizes what I'm plugging in. It's not that big of a deal, but I like to cancel a few things if I can. All right, if I've plugged this in correctly, which is a big if at the moment. So this is a small number, 1.1 times 10 to the negative 14. This is a weak magnetic field. As far as units are concerned, in the denominator down here, we squared these meters. So meters squared will cancel with the meters up here and the meters up here. So the meters are gone. We have Teslas and amps, but remember an amp is a coulomb per second. So the coulomb per second cancels with the amps, and we are left with Teslas. And we use a capital T to represent that. And yes, this is the same as the car Tesla, only, of course, Nikola Tesla came first. So named after him. This here only gives us the magnitude of the magnetic field. Magnetic field is a vector, so we do need the direction. That comes from the right hand rule. I'm going to abbreviate that as RHR so I don't have to write out the whole thing all the time. To solve the right hand rule, take your thumb of your right hand and point it right, to your right. The velocity vector. So we're holding our thumb up to hold it and point it in the direction of the velocity. So if you put your hand up in front of your face with your thumb pointing to the right, your fingers, okay, let's see if I can pretend to draw this. So thumb, and then our fingers up here, if I just relax my hand and let my fingers, wow, okay, don't judge me too much, please. Those are my fingers. That's okay. Thumb of my right hand is pointing to the right. I would see my fingertips. I could look at my nails on my fingers right here. My fingertips are in general pointing towards me up there. Since my fingertips directly above my thumb, because that's where point A is in our picture, my fingertips point out or point towards me above when I'm holding them above my thumb. That means the magnetic field directly above my thumb, directly above this velocity, points out towards me. We would say in terms of the picture, out of the screen, to describe it in terms of the picture we're looking at for the problem. So this magnetic field is not particularly strong, but it is there, of course, and the direction points out of the screen. If point A had been below the charge, so we still had this charge moving to the right, but point A was down here, the same distance. The magnitude would be the same, but thinking of the right-hand rule, I have to kind of contort my hand. So I still have my thumb pointing to the right, but I need to think about my fingertips being below my thumb. So I would be holding my wrist down this way, and I would see my fingers curling away from me. Fingers would point away. Now that's a weird contortionist thing to try to do, to try to look at the back of your hand, keeping your right hand such that the thumb still points to the right, but have your fingers below your thumb. That's kind of a hard position to get in. My fingers would point away though, which means the magnetic field at this point, it would have the same numerical value, but it would point into the screen. So a big thing to remember, the magnetic fields always make circles around the charges. So if it comes out of the screen on the top, it has to go into the screen on the bottom to complete the circle. We'll do more examples, and I'll turn on my video if needed to better explain that. So this right-hand rule, Your fingertips are just representing the direction that is tangent to the circle at any given location. So at point B in our picture, I'm going to erase this so I can draw. So point B, actually, let's keep blue for a second. R is different for point B. Our hat will point along the line of R. And so now we're going to have an angle between our hat and V that's not 90 degrees. Okay, so point B. R is now going to be the square root of 3 millimeters squared plus 3 millimeters squared. Since I chose the same dimensions up here, I know the X and Y side. So 4.243 millimeters. That's the distance from the charge to this point B. The angle phi between R hat and V. If I draw my picture just down here, R and V, that's the angle I want. The angle, though, is based off our R, our distance from the charge to point B we just found, right? The x squared plus y squared square rooted. So the 3 millimeters and the 3 millimeters. This angle in here, since I have the same dimensions, this angle in here has to be 45 degrees. I could find that. I called this a theta. The tangent would just be the x side over the y side, the opposite side over the adjacent. I just know, since these are equal length sides, that that's going to give me 45 degrees. The angle I want in my equation is relative to the velocity, which is to the right. So our angle in this case is 45 degrees. If this angle in here had been something different, then we would have just said 90 minus theta to get phi. So phi is always the angle between the velocity vector and then the r hat vector, which points from the charge to where you're trying to find the field. Okay, I'm going to plug in to B. So here, let's scroll a little bit. So just using this equation that I have boxed up here to find the magnitude again, mu naught, I'm using the exact value because that's what I remember. V, I said, was 6 times 10 to the 6th. Our angle here is 45 degrees. And then the distance we found to be 4.243 meters. Oops, I need that in meters. So, times 10 to the negative 3. And we'll square that. 4 pi's cancel again. So I just have 1 times 10 to the negative 7. Oops. So I'm getting 3.8 times 10. That doesn't make sense. Okay, sorry, let me run that through again. All right, so 3.8, I put a power in somewhere wrong, one of my 10 to the somethings, because I originally got times 10 to the negative 9, which wouldn't make sense because that would be smaller. So it would give me a stronger magnetic field than at point A, which doesn't make sense. The magnetic field is going to be weaker farther away. So plugging it through again, 3.8 times 10 to the negative 15. So the field is weaker at point B, which should make sense because it's farther away. Now, the direction. When we're at a point, so point B up here, R hat points towards it, V points to the right. It still turns out that we can put our thumb in the direction of V and our fingers curl around. Since our fingertips point out of the screen or towards us at point B, we still have the direction as out of the screen. This right-hand rule we're using is actually based off of the right-hand rule for cross products. The right-hand rule for cross products, if we look at our equation in terms of vectors, B, so I'm going to just write it on the right here, the direction is determined by the direction of V crossed with R hat. Any cross product equation at all. In fact, if you've taken statics, you've done this with your torque equation as well. The way our book is explaining it, we're still putting our thumb in the direction of V. So hold your hand out where you have your thumb pointing out, your index finger pointing straight out like you're pointing at something, and the rest of your fingers pointed perpendicularly to it. So index, finger, thumb, your middle finger essentially. In this orientation, if our thumb is in the direction of the first vector in the cross product, we need to put our index finger, our pointer finger. So pointer in the direction of the second vector, our middle finger will be the result, the direction of the answer. I typically do it in a semi-different order, but as long as the order is correct, we're good. We can do the thumb, index, and middle. So in this case of point B, if I put my thumb in the direction of the velocity, which is to the right, and I put my index finger as best as I can in terms of R hat, if we think of the R hat vector, it has an X component and a Y component. It's really only the Y component we care about. Our middle finger would point out of the screen. So it circles the same similar way. That circling, this right-hand rule, using the circles down at the bottom, comes from the cross-product right-hand rule. It's essentially the same thing. Which now I assume you're probably like, what the heck? So we're going to do some more examples with finding directions. Finding the magnitude of the magnetic field of a moving charge here is not very hard. We need to know its charge, how fast it's moving, how far away we want to know the field. It's these directions that end up being a little more confusing at times. But with practice, with the right hand rule, it can come with practice is what I'm trying to say.